Swayam Prabha. Digital India. Educated India.
Right? So we just recall what we are doing. The idea was I have a set of points, n points in general position, like affine independence. Any d plus 1 point will be set, subset will be affinely independent. This point set is in Rd, and what we want to do is we want to look at two things. We want to look at lower hulls and we want to look at upper envelopes. We want to look at lower hull of P and we want to look at upper envelope of P star. Okay. And what we want to show is they are dual complexes. Okay. So what was the definition? You want a bijection between the complexes such that if you have a k dimensional simplex, k dimensional face here, you will get d minus k dimensional face here, right? That was the definition. Good. By the way, what is the dimension of the lower hull and upper envelope? Before we begin the proof, this is d minus 1 and this is d minus 1. Okay. So this is, just check yourselves. This is not hard to check. Okay. So now the main idea is, the main thing is we want to prove that they are dual to each other. So again, the assumption we will be making is point set P is such that P and P star are in general position. Position with respect to points and hyperplanes respectively. Okay. So now let's look at a face of a, let's look at a face of a lower hull. Lower hull P. Let's look at a face of a lower hull. So it's a face of the convex hull, right? So it should be equal to convex hull of some subset of points from P that we proved, right? Polytopes faces will be like that. Okay, so it will be some convex hull of, so without loss of generality, let's assume it will be some. Okay. Since this is a face of, it's a face of convex hull of P, what do we have? There exists a upper, there exists a, what was the term you were using? Non-vertical. There exists a non-vertical hyperplane H such that H intersection P is equal to the set P1 to Pk, and the face sigma is equal to, basically sigma is also equal to H intersection convex hull of P, which will be equal to convex hull of this k points. Yeah, this is from the results we proved last class, right? Good. So this is the face. So let's take a point. How should I take? Okay, so this is a face. Okay, so now let's look at the duals now. So let's look at P1 star, P2 star, Pk star. So okay, so just for simplicity, let's take it to be k plus 1 points. Okay. So, what will be the dimension of sigma? By the way, dimension of sigma is k, right. I will map it to a d minus 1 minus k dimensional face of the upper envelope. That is the goal. Okay. So, now let us look at this set of dual hyperplanes, okay, and also look at this dual point H star. See, P1 belongs to H, P2 belongs to H, dot 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 Pk plus 1 also belongs to H. What does that imply? H star belongs to all of these intersection, right, intersection I equal to 1 to k plus 1 Pi star yes, no. Okay. So, now let us take another point Pj. Any question? Let us take another point Pj, which is not Pj, where j is not equal to one of these k plus 1 points. Okay. So, let us go to the next page. Okay. So, again let us try to see it from this side. Okay. See, one side of H, it's okay. This the AC got on, that's why the anyway. So, only for me, I know. So, one side of the positive side of H contains your convex hull, right? Is it the case or not, right? That is how we have defined, right, and we are taking like the positive side are the ones we are taking anyway, those are the ones we have taken it, right. So, okay, so this is how your convex body will look like somehow, like this convex hull of P. That means, and these Pi's where I belongs to, for all these P1 to Pk, k plus 1, and let us say this is H, this is H plus this region. Okay. All of this P1 to Pk plus 1 belongs to this hyperplane H. Any other Pj can be inside, Pj can be here. Okay. It's a convex hull, right, can contain points inside also, right. So, all the points Pi does not have to be vertex of the convex hull, right, but that whatever be the point Pj has to be in H plus, has to be, right. So, Pj has to be H plus if j is not equal to 1 to k. So, what does that imply here? Pj star, so let us see. So, it implies that for all Pj where j does not belong to, so when I write box it means 1 to k, implies Pj belongs to H plus. How did we set the duality? The duality results, we have set it up in such a way that this also implies that, this implies that H star has to be in the positive side of P star j. Pardon, can you come again? Yeah, so that's j belongs to box of k plus 1, yeah. So, think what is happening actually. So, see, now we have this object intersection of these hyperplanes. In the proof, if you remember, since we have set it up in the general position assumption, if we can show that this intersection with the upper envelope of P star is not equal to empty, we will be done. Why? This is something I mentioned end of last class. Okay. Faces of polyhedrons are determined by intersection of the hyperplanes supporting the half spaces, and if it has a non-empty intersection with the polyhedron, right, then it will determine a face. And if they are in general position, if the hyperplanes are in general position, then what will be the dimension of that face? D minus the size of the D minus the number of hyperplanes that you are using it, right. So, if I can show this intersection, this is non-empty, so the face that this thing will generate will be of dimension D minus K minus 1, which is I can rewrite it as D minus 1 minus K. So, I have a map that takes a K face, a K simplex to a D minus 1 minus K dimensional polyhedral face, right. But this only holds as long as I can show the intersection is non-empty with the upper hulls, right. This has to be non-empty. But see, for all Pj, so but what is your what was your like okay, just one second. Yeah, upper hull our envelope, sorry. So upper envelope was basically the lower faces of this object Pt star intersection T equal to 1 to n. Right. So does it have a non-empty intersection or not? This point H star belongs to all of these is lies on the hyperplanes Pi star, and it is in the interior of the other half spaces. This obviously belongs to this object, right. For 1 to K plus 1 Pi star, it is on the bound, it is on the hyperplane. For the rest, it is interior. So obviously it belongs to the intersection. So using that result, we get a face on the upper envelope. So we get a mapping from a K simplex is going to a polyhedron face of dimension D minus 1 minus K. Okay. So this general position assumption on this side, it's not that serious. You can work around actually this, but it is easier like to write the proof. It is easier we assume this. Okay. Okay. So now this is one way we have done, right. It is going from your convex hull to lower convex hull, lower hull to the upper envelope, right. Lower hull to the upper envelope, UP star. Okay. Now I have to go the other way also. How do I do the other way? See, how will a polyhedral face of UP star look like? So means, so let's say there it's a, so take some face here, okay, that belongs. That means there exists some set of points, okay, some hyperplanes such as sigma is equal to so let me write, so I take this and let's say there exists then some P1 star, what should I write, not P, yeah, let's say without loss of generator I am assuming from 1 only, P2 star some pt plus 1 star. Okay, let's say this is a t dimensional sigma. If it is t, then it should be t exactly, d minus t. Sorry, is it? Just 1 second. So let me check. D minus yes. Okay. So if this is a d dimension, if the dimension of sigma is t, then you will have exactly dt hyperplanes whose intersection is non-empty, right? And their intersection with this object, let's call this object t for the rest of this thing. So t intersection of this I equal to 1 to t pi star is not equal to empty. My definition, faces will be generated like this. As I said, right, any face will have a corresponding set of hyperplanes, right? This is a theorem that we discussed last. Now again, what you do? How do you find the corresponding simplex? You should take the vertices here, right, and do the same calculation. It's okay. Okay, so one thing, okay, you take something here, but you see here what did I need? To generate this thing, I needed a point H star that belongs to the intersection of the hyperplanes P star T, where P star J, where J belongs to 1 to k plus 1, and that H star also belongs to the interior of the other hyperplanes, like interior side of the other half spaces, right? So I also, so here I have given you the points, I need a corresponding hyperplane, right? Because to generate faces of the convex hull, I need a hyperplane also, right? How do I generate faces of a convex body? I need a supporting hyperplane. Here I am getting the vertices, but these vertices has to lie on some hyperplane. Here, if I take the dual, I get a corresponding vertices, but I have to show, okay, there exists a hyperplane on which only these vertices lie, right? How do I do that? Any guess? Take a point here. This H star, X star, not X, let's say, right, Y, let's say. This Y star will be the corresponding hyperplane on which these points will lie, P1, Pt. Okay? And Y star plus will contain rest of the points. Then you will get the plane. Okay? Good. So by the way, what will be the dimension of the simplex here? T minus 1. So am I making some mistake when I do this? It is not, right? Because d minus t, you should write it as d minus 1 minus of t minus 1. Right? Dimension of the dimension of upper hull is d minus 1. Right? So it's okay. D minus 1 minus of t minus t minus 1 is going to a t minus 1 simplex in the lower hull. Upper envelope to lower hull. Okay, I will like take a minute and see if there is some confusion. If you have some question, ask. Do you want me to repeat the argument again? Okay, so let's do the argument again. Okay, so let's go back. So again we are assuming P and P star. So okay, P and P star are in general position, right? And I look at the lower hull, took out a simplex from the lower hull. I know this simplex is on the boundary of the convex cell. It is a face, proper face of the convex cell. It will be generated by what? Some supporting hyperplane. The supporting hyperplane will be non-vertical, because that is how I generate the lower hull, and the positive side of the lower will contain the rest of the convex hull, right? Definition. So, it is okay. So, let sigma be convex hull of P1 to Pk plus 1, right. So, H intersection P point set should be equal to P1 to Pk plus 1. H plus contains other points. Okay. Also, sigma is equal to H intersection convex hull of P. Okay, good. Now, I start with a k dimensional face of the lower hull. I want to generate a d minus k minus 1. So, d minus 1 minus k dimensional polyhedron face of the upper envelope. How do we do it? We want to use duality. Okay? We will take the points P1 to Pk plus 1 to the corresponding dual hyperplanes. Okay? See, by the way, there is no magic happening here, because the upper envelope is anyway generated by this Pi star greater than equal to 0, like Pi star greater than equal to 0's lower boundary, right. That is the upper envelope. So, it is not surprising that we have to take dual of these points. That is how we set it up, this problem, right. So, we take that, we take this hyperplane H to H star. H star is a point. What we notice? We notice that H star belongs to intersection of Pi star, where I is from 1 to k plus 1. It belongs to all of these hyperplanes. So, the intersection of this hyperplane is non-empty. But see, just because H star belongs to this, that does not mean this intersection will generate a face in your upper envelope. It has to have a non-empty intersection with the upper envelope, right. So, what did we show? Actually, H star lies in the upper side of all Pj star, positive side of Pj star. So, that shows that intersection of, but did we prove that? Let me go down. Yeah, so that shows that intersection of this and this is not equal to empty. Once we have this, we invoke the theorem that we studied last class, end of last class, and this gives you the face that we are looking for, polyhedron face that we are looking for, and of the dimension that we want. Okay, by the way, the dimension the one we want is following from the fact that I am assuming P and P star are both in general position. P is in general position with respect to points condition, P star is in general position with respect to hyperplane condition. This intersection will generate a face of dimension d minus 1 minus k if P star, the hyperplanes are in general position. Okay? Otherwise, it won't. Okay. Similarly, what you do? You do the other construction also. It's okay? No, just one. Oh, UP star it should be, no? Okay, so now we will do this, we will first study Voronoi diagram in terms of this framework, Voronoi and Delaunay in this framework. Okay, so let us again start with the point set P, P1. Okay, so here now I will assume that stronger general position assumption, which was this has to be any subset of size d plus 1 or lower will be affinely independent, and no sphere in RD contains d plus 2 more than equal to d plus 2 points. So, any sphere in RD will contain at most d plus 1 points from the set P. Yeah. So, the stronger generalization assumption was basically that. I will assume now for the rest of this. Okay. So, let us say even let us step back one before that and see, can we look at this Voronoi diagram in some different way. Okay. So, this is something Arijit Vishnu also introduced, like minimization of a function framework. Okay. So, let us say you have family of functions f1 to fn, okay, all continuous functions from Rd to R. Okay. Let us define f to be minimum over all I belonging to 1 to n f of x f I of x. Okay. So, what is happening? So, let us look at the graph of this functions. So, basically you have this Rd below. So, let me drawing with a line only, so as if line represents Rd. So, you have Rd here, this is the direction where the value of the function is being taken. So, you have a function f1, then you have another function f2, f3, f4, like this. Okay. So, how does the graph of this function fx look like? These are the different color curves are the graph of the functions fi's. How does the graph of the function f looks like? It will be something like this, right? It is minimum, right? So, it will be right. This will be the graph of f. Yes or no? Okay. Good. So, now what I want to do is, for each point x in Rd, I want to define an index set. So, I of x I want to define. This is equal to all those i's such that f of x is equal to fi of x. Okay. Makes sense what I am trying to define? Okay. So, what will be the index of this x here? So, we go up, it is basically, what was this, f1 I think. This will be f1, right? Just f1. What about x here? What will be the index? Just 1. So, what will be the index set of this point x? So, let us call it x1, this call it x2. This will be, do not call it f1, f2, call it just 1 and 2. So, we want it to be indexes. So, similarly, there may be the case where 3 of the functions are getting the value. So, you get an index set. Okay. So, these things are what are called. Pardon? Can you come again? Yeah, so index set is not a singleton thing. Yeah. So, what see, it is defined in the following way: all those i's such that fx is equal to fi of x. You know, many functions are of the same value at this point. The minimum value is attained by many functions at that point. So, the index set will be that big. These things are called lower envelope of FIs. So, but we can also define in an analogous way upper envelope of FIs and a corresponding index set in the same way, right? Good. So, let us again go back to the definition of Voronoi diagrams. Okay. So lower will be the minimum, upper you will replace it with max. So, upper I am not drawing, it is so hard to draw with these horrible functions that I have drawn. I will draw for a very nice one which is easy to do. Same FIs, yeah. You have a family of functions, you have defined the upper envelope will be just basically a function which will be, so yeah, so let me write it formally. So, let us say you have some family of functions, continuous functions defined over all of Rn. So, the upper envelope for this set will be max g of x will be max of over all I in 1 to n gi of x. That is it. Okay. Good. So, this is something actually Arijit Vishnu did introduce. Okay. So, I will. So, now let us look at the Voronoi diagram definition. Okay. So, let us say a Voronoi, let us talk about a Voronoi cell of a point pi. What is that? All those x such that d of x comma pi is less than equal to d of x comma pj for all pj belonging to p. Okay. Now, look at these functions. For pi, I associate the function x minus. So, I am looking at the square of it, it does not matter, you can take cube, square is easier, nicer, it will give a paraboloid. So, this is what we want to do. Okay. Okay. So, let us say see Voronoi diagrams can be defined in different ways. One way is if I give you an x in RD, you should tell me what are the PIs. So, what are the PIs inside whose Voronoi cell x lies? If somehow I can answer this question, your data structure can answer you this question. You are basically answering, you are basically storing somehow a Voronoi diagram, right? Given any point, I can tell you what are the Voronoi cells where this point lies. So, what am I storing basically? I am storing the Voronoi decomposition of the plane for the points using the point set P basically, right. Okay. So, now if I associate for each point x in RD this function. So, let me not write exponents for each point pi this function. Okay. So, x goes to x minus pi square. So, this is your Fi. Okay. Now, what I do is the following. I maintain, so these are Fis of x. So, what I want to maintain now? I want to maintain f which is equal to minimum over all I belonging to 1 to n Fi of x. Let us say I can maintain this. How do I maintain it? What I can do is give me any x belonging to Rd, I can tell you the index set of that point x. You get what I am trying to do? Give me any x in Rd, I will able to tell you what is the index set of x. So, what is this index set telling me? The set of points, indices of the points whose Voronoi cell contains x, right. So, basically what? So, you have this different paraboloids, okay. Fi's are these different paraboloids, and what you are storing, I am kind of maintaining this lower envelope. Not only am I maintaining this lower envelope, I am somehow know what are the index set of each point. Somehow I can compute fast the index set of each point. That means I am kind of storing the decomposition of the Euclidean space Rd with respect to the point set P, right. So, this is the way we want to look at. So, this is the minimization version. Let us look at a maximization version of this. So, if I maximize, what will it give me? This is will give me the Voronoi diagram. Also, sometimes when normally when you say Voronoi diagram, people mean closest point Voronoi diagram. Okay. But if I take max, what will it give me? Has this been introduced? Furthest point Voronoi diagram. So, this gives you what is called furthest point Voronoi diagram. Okay. I do not want to discuss it now, but there is something called furthest point Voronoi diagram. Have a look. If I can computing rather than mean, compute max, okay, it will give me furthest point Voronoi diagram. So, if I just you can just define the Voronoi cell of in the furthest point Voronoi diagram. A Voronoi cell of a point will store all those points whose following inequality will be true. The distance to that point should be greater than or equal to the other points, distance to other points. This also gives you a decomposition, by the way. That computation is nothing but maintaining the upper envelope of the function and the corresponding index set, this index set. Yeah, and any kth order will be a kth level decomposition, but I do not want to get into it because we have to, but yeah. So, this frameworks captures this, like especially this Voronoi decomposition in terms of distances, this captures. Okay. But see, this when you go to higher dimension, maintaining this envelope, quadratics are costly. I mean, I do not want to maintain normally quadratics. Okay. I mean, maintaining linear is hard enough. Okay. I mean, so I will prove a theorem, but like there is something called upper bound theorem. So, what will be the, so if I give you n half spaces in Rd, okay, what will be the like how many vertices will the polyhedron have, where the polyhedron is the intersection of these half spaces? We should be interested in that, right? We want to know what are the vertices. I am not asking all the faces also, I am just asking all the only the vertices. It will be n to the power d by 2. It's that big, it grows very fast in terms of d. For fixed d it is okay, but if like d is also growing, n to the power d by 2 is hard. But here we are only using linear objects. Now, quadratic will be even more complicated to keep. Okay. So, somehow I want to recapture this Voronoi diagram thing, okay, via some kind of a linear diagram, okay, some kind of a linear envelope. Okay, even before I do that, so let us look at this diagram itself. Okay, so here, so have a look. So this part, so let me call this. What will be the label of this part? So let us call this 1, 2, 3, 4, 5. So sorry. What is it? What happened? I don't know. 5. Okay. What is the label here? Index set 5. Here the label is not 5, sorry, 1. What is the index set label here? 1, 2, here 2, 3 like this, right? Inside here it is just 2, right? But if I can maintain the lower envelope, actually now if I project, see this lower envelope is maintained in RD plus 1. If I project this on RD, the lower RD, okay, I will just basically get the Voronoi diagram. But see, even that, like if you think through it, let's say I want to compute, somehow I know how to compute the lower envelopes. To project lower envelope of a quadratic over a flat, that itself also over another RD, that also is complicated. So I ideally don't want to do these things. Okay, I want to work with planar objects, like flat objects. Okay, so how do we do it? So let's go back again in the definition of Voronoi diagram. So let's say X belongs to the Voronoi cell of Pi. Okay, what does that mean? That X minus Pi square is less than equal to X minus Pj square. So this means minus 2 X dot Pi plus Pi square is less than equal to minus 2 X minus X comma Pj dot product between X and Pj and Pj square. Right, I just cancelled the norm square of X from both sides, right. So can you see a linear equation that I can use? So if I set Fi's to be equal to 2 X comma Pi minus Pi square, okay, and I maintain the upper envelope of Fi's. Did you get what I am trying to say? So now I define F as equal to max over all I belonging to 1 to n Fi of x. Fx is equal to this. This is basically upper envelope of Fi's. What will it store? The Voronoi diagram again. But what is the good thing about this? These are linear inequality. These are hyperplanes, right? These will be hyperplanes. So if you think about, so let's say you are in this RD, and you have defined x of d plus 1. So let me define it properly. So x of d plus 1 is basically equal to 2 times x dot Pi minus Pi square. Okay, this thing. Simplify it further. X d plus 1 minus 2 x comma Pi plus Pi square equal to 0. What is happening here? So I am getting a non-vertical hyperplane. Good. If I have a point in RD, okay, where does that point go to? So let me do it in the next page. Okay, so let's do it again. Okay, so what was I trying to do? I was saying, see, x of d plus 1 is equal to, so for this just Fi I am writing, right? It will be x comma, so let me, Pi minus Pi square. Okay, so this will be give me hyperplanes, non-vertical hyperplanes, right? Okay, and what am I trying to maintain for these non-vertical hyperplanes? Lower envelope. Sorry, upper envelope, right? Because I am doing max. Max is storing the Voronoi cell. So if I think of this as an hyperplane Hi, so what am I basically storing? lower upper envelope. So, so these are HIs. So, I write again, I write this set HIs as I equal to 1 to n as capital H. So, if upper envelope of H is what we are calculating, right, this thing, right, but this is still better than, this is, by the way, this is a convex set, polyhedron, something that we, I mean, if we cannot maintain even this, then anyway there is no hope of maintaining quadratic. So, forget it. Even this can sometimes be hard when you go in high dimension, but even if you cannot maintain this, then the higher one is hopeless, no chance of maintaining. Okay? But this should be easier thing to maintain. But this keeps track. So, if once I maintain the lower envelope of this object, upper, keep saying lower, upper envelope of this object, okay, I basically maintaining the Voronoi decomposition in RD. How do I get it? I project this upper envelope to RD and I will get my respective Voronoi diagram. Okay. So, now what do we get? We have now mapped Voronoi diagram to lower envelope of these hyperplanes, non-vertical hyperplanes. Okay. So, let us look at this hyperplane slightly more closely. What kind of hyperplanes are we looking at here? These hyperplanes that we are looking at, what are the hyperplanes actually we are looking at? See, can you see this hyperplane, this one, this object, this HI, this one, come again, what was the question? This hyperplane, can you see passes through this point in RD, pi comma norm of pi square, which belongs to RD plus 1. Can you see this point belongs to HI? Just substitute. It does, right? See, this when I write x, this point is in RD, by the way. This is not in RD plus 1, right? So, if you look at this point exactly lies on this hyperplane. Where does this point lie on? In the paraboloid in RD plus 1. Remember that paraboloid we were looking at? X of, so let me write the equation of the paraboloid in dimension d plus 1. So, it would have been like something like this, is d plus 1 is equal to summation I equal to 1 to d x I square. This point lies here, right? See, pi belongs to RD. So, what are we doing here? So, we have this point things in RD, I am lifting them up. So, here we have these points, I am lifting them up on the paraboloid. Okay. Then what we are doing? Then we are finding the tangents at these points, right, and we are computing the upper envelope of these tangents. Okay. Okay. So, a natural, see, when we were doing Voronoi diagram or Delaunay triangulation in R2, to find the complexity of it, it is not that hard, right? I mean, you basically get a planar graph, use results from planarity and get like what will be, how many faces will have, how many edges will have, how many, these things you can calculate, right? How many triangles will you have? You can get an estimate, right? But when you go to RD, what if I say, can you tell me what will be the complexity of the Voronoi diagram. It's not obvious how to bound the complexity. It's partitioning RD. There are 100 different ways to partition RD. I mean, there may be very bad ways of partitioning RD, there may be very good ways of partitioning RD. How do I exactly calculate? Okay. So, let us say I give you this theorem as a black box. This is what is called upper bound theorem. Okay. Which says that if you have a polyhedron P, which is basically intersection of some set of half planes, n half planes in RD, okay. And I tell you that the complexity, combinatorial complexity of P is then will be bounded by order n to the power float d by 2. Let us say I give you this as a black box. Do you get what I am trying to say? Okay, so this is a black box kind of a result for the time. We will see a proof in the tutorial today. Okay, but assume this as a black box. So, if you have a polyhedron in RD defined with n half planes, then its combinatorial complexity is this. Okay, can I use that to get the complexity of the Voronoi diagram? Should we, no? Why should that be the case? What we have here shown is Voronoi diagram is nothing but the lower envelope of a family of vertical, non-vertical hyperplanes in R d plus 1. So, what will be the complexity? You should say it will be bounded by order n to the power d plus 1 by 2 . So, this is basically order n to the power ceiling d by 2. Yeah, it will become ceiling now. See, if d is even, you just check. I mean, this is nothing fancy happening here. Okay. So, if this result is known to us, assuming we know this result, upper bound theorem, this is a very important theorem in this geometry of polytopes and all this. This was proved by Peter Macmillan. It was an open question for a long time, then he proved it. We will see a proof. What he showed was even, so he was able to calculate very tightly how there is something called phase vectors of polyhedron and how the phase vectors look like. So, forget about those things. We will be looking at the crude upper bound. Can I prove the crude upper bound? In the sense, I want to prove the number of vertices of P will be bounded by this. We will see a proof of that today. Okay. For the time being, do not have to worry about it, but at least now we know how to calculate the complexity of the Voronoi diagram in RD. Okay. Good. So, let us now move to Delaunay. So, let us call it triangulation only. So, this is what we will be looking at now. So, how much time do I have? 8 minutes. So, let us again just recollect the definitions, the theorem we will prove, we will come back. So, what is the Delaunay triangulation? We have defined it in number of different ways now. One way is nerve. Okay. So, one thing, okay, let's try to prove this. Okay. So, you have some set of points and I have drawn its convex hull. Okay. So, by the way, so the way we have defined is what? We said sigma will belong to the Delaunay triangulation of P if say sigma is equal to the set P1 to P k plus 1, then Voronoi of Pi's intersection I equal to 1 to k plus 1 is not equal to empty. It is not P, sorry. Right? This was the definition. In terms of the nerve, this was the definition of the nerve, so both ways, right? If it is non-empty, then sigma will belong. If sigma belongs, then this is happening. Okay. Okay. So another way to look at it is saying sigma will belong to your Delaunay of P if there exists C belonging to R D and R belonging to such that ball centered at C comma R. So, I am talking about this is an open ball. When I write B C comma R, this means all x such that distance between C comma x is less than R, okay, is empty. Empty means no points of P are contained inside this open ball, and this is condition 1, and boundary of the ball, okay, boundary of the ball contains the vertices or Pi for all I belonging to 1 to k plus 1. So, what is happening? You have k plus 1, you have k plus 1 points. These k plus 1 points are on the boundary, okay, and the interior of the ball is empty. See, I am not saying that these are the only k plus 1 points that are on the boundary. There may be even more points. That is a separate question to look at. What I am saying is at least these k plus 1 points should be on the boundary of the ball. Okay? So, why should we make this distinction? I want to make this distinction because, see, as we said, like the non-emendability of Delaunay when we are talking about, with having 4 points on the corners of the square. See, if I take the center of the square and make a circle, even though this does not look like a circle, this is a circle, I assume. Okay. So, so I told you what, this is P1, this is P2, this is P3. I said P1, P2, P3 belongs to your Delaunay complex, right. This is the center, and whatever be the radius, I do not know, like square root 2 or whatever, square root 2 by 2, whatever. Okay. So, but this also this circle also contains P4, right. That is perfectly fine. In terms of our definition, it is not violating our definition, right. This means P1, P2, P3 is in the Delaunay complex, P1, P2, P4 is in the Delaunay complex. All subsets of these 4 points are in the Delaunay complex basically, right. So, we will, but the thing is, now when we assume general position assumption with respect to affine independence and no sphere containing more than d plus 1 points, this will not happen. Okay. What will happen? See, any circle or any sphere will contain at most d plus 1 points. Okay. So, we will build on it from the next class.